Fractional precipitation allows us to separate certain ions by making use of the Ksp values. For example, we have a solution that contains tin and zinc and it's saturated with H2S. We want to know the values of hydronium ion concentration that will allow only one of these ions to be precipitated. Now we're given the Ksps for tin and for zinc sulfide. So what we're going to do first is calculate the value of sulfide ion that will make the ion product equal to Ksp. So for tin, we know Ksp is equal to the concentration of tin ions times sulfide ions. Ksp is 1 times 10 to the negative 25th. The tin ion concentration is 0.1, and so we can solve for the sulfide ion concentration, which comes out to 1 times 10 to the negative 24th molar. We're going to do the same thing for zinc. Ksp for the zinc is equal to Zn times sulfide. Ksp for the zinc sulfide is 1 times 10 to the negative 21st. Concentration of zinc ions is 0.1. And so that will allow us to solve for sulfide ion concentration for the zinc solution, which comes out to a value of 1 times 10 to the negative 20th molar. So this tells us that as long as the concentration of sulfide is less than or equal to 1 times 10 to the negative 20th, but greater than 1 times 10 to the negative 24th, only the tin sulfide will precipitate. It will leave the zinc in solution. But I don't want the sulfide ion concentration. I want the concentration of H3O. That will allow this to happen. This is a saturated solution of H2S. H2S is a diprotic acid. So H2S, when it reacts with water, will form H3O plus HS minus. My Ka1 value for H2S is 1.110 to the negative 7. That HS can further react with water to give me H3O plus sulfide. My Ka2 value for this acid is 1 times 10 to the negative 14th. So we can control the sulfide with hydronium. We're going to multiply Ka1 times Ka2. So Ka1 is 1.1 10 to the negative 7 multiplied by Ka2 10 to the negative 14th. My expression for Ka1 is H3O times HS minus divided by H2S multiplied by the expression for Ka2 H3O times sulfide divided by HS minus. And we can simplify this because the HS's cancel out, and when we multiply the numbers we get 1.1 times 10 to the negative 21st is equal to H3O squared times sulfide over concentration of H2S. The concentration of H2S is constant in a saturated solution, and it is 0.1 molar. So this number down here is constant. We have solved already for the concentrations of sulfide Now we just have to plug in those limits. So for the lower limit, concentration of sulfide is 10 to the negative 24th. So we have H3O squared. We're going to plug in my sulfide ion concentration as 1 times 10 to the negative 24th. And the concentration of H2S is 0.1 in a saturated solution. And we're going to set that equal to 1.1 times 10 to the negative 21st. And so we can solve for H3O. Comes out to a value of 10 molar. That's the lower limit. The upper limit, we're going to solve for H3O again. Same equation, H3O squared. The lower limit was 10 to the negative 24th. The upper limit is 1 times 10 to the negative 20th. It's still 0.1 for H2S. And that's equal to 1.1 10 to the negative 21st. So for the upper limit, the concentration of H3O comes out to a value of 0.1 molar. So there are my upper and lower limits. So here's what that tells me. As long as the concentration of H3O is less than 10, but greater than or equal to 0.1, only the tin sulfide will precipitate. So that's called fractional precipitation, precipitating one ion while leaving the other ion in solution.